Okay, our next application of the integral is going to be calculating volumes. And let me show you how that's going to work. Consider the following. Let's say, for the sake of argument, that we have the basic squaring function from pre-calculus. Oops, it should be curved, right? Okay, and let's say that's going to go from, we'll say 0 to 1, 2, 3, 4, 5, 6, 7. So it's not going to be to scale. All right, notice that the graph and the x-axis trap the following region. Now, we saw in the previous lectures that we can calculate the area of this region using an integral. Okay, so that's something we're accustomed to right now. The differential element of area, gang, here's what that would look like, right? Okay, remember our very thin rectangle? And what do we always do? Once we draw the representative or the differential element of area, in other words, the thin rectangle, we always label it, right? Top and bottom. Okay, I won't bother with the bottom because it's resting right on the x-axis. Okay, all right, and we know that the area of this can be found by taking the difference of the y coordinates to get its length, and then we multiply it by its width, which is dx. So I'm just going to make a note. I'll just say here, the area of that rectangle is going to be x squared times dx. Okay, and then we would sum up all those elements as x ranged from 0 to 7. But here's what we want to do this time. Imagine taking that entire region and revolving it around the x-axis. Okay, so what would that look like? Well, let's see, the curve would come down something like this, right? It would almost look like the end of a trumpet, right? Something like that, but it would be a solid, okay? The whole thing is a solid. It's not a perfect cone, right? Because it would have curved sides, but it is a solid, like maybe a paperweight or something. And the question for us is how to calculate the volume of such a solid. Gang, these solids are sometimes referred to as solids of revolution, okay? Because they take a region and you revolve it around an axis, okay? Sometimes referred to as the axis of symmetry, if there is any, okay? But there doesn't have to be. So, but otherwise, we just refer to this, in this case, the x-axis as the axis, okay? So how to do this? Let me make a remark here, just as a reminder. If you look in the front or back cover of your books, there are certain geometric shapes that we should all be familiar with. One of them is a right circular cylinder that looks like this. Okay. Now the volume of such a cylinder is equal to pi r squared h. Okay. And what's the pi r squared? Well, you recognize pi r squared as the area of a circle, right? So you know what that is, gang. That's the area of this base down here, right? That circular region down there, that's a circle whose area is pi r squared. So that accounts for this right here. And then you just multiply that by the height, and that gives you the total volume of the shape. So why do I mention this? What's this got to do with anything that we're talking about? Well, if you go back and look at the figure, okay, we're going to take the entire shaded region and revolve it around the x-axis. But let's consider just rotating the one red rectangle so it doesn't get too busy. Okay, so let me do this. Let me take off this piece and this. Okay, and we'll just consider rotating the red rectangle. Well, if I rotate the red rectangle around the x-axis, here's what it's going to generate. okay? And what that is, gang, you know what that is? It's one of these things. It just happens to be laying on its side, okay? So like think of a quarter, right? It looks like that. It's a circular disc. It's not a circle because a circle only has area and no depth. This is an actual cylinder, okay? It's got a thickness to it. The question is, what's the thickness also, right? So I'm going to make a note here. The volume of this one disc, let's call it, now remember, it's really, really thin, gang. So just like the area of the rectangle is dA, let's call the volume of the disc d capital V, all right, d capital V. And because it's a cylindrical surface or cylindrical solid, just like the one to the right, its volume is going to be equal to pi times the radius squared times its height or thickness. I would rather we use the word thickness in this case because it's not a very tall cylinder when you think about it. It's really thin. So what would its thickness be? In this case, it would just be dx. Okay? All right, let's see. Now, the radius, what's the radius going to be? Well, the radius is this vertical distance right here. In fact, gang, it's the length or the height, in this particular case, of the rectangle that created it. Okay, that distance from the center to the top of the rectangle. Well, you know what that is? That's the y-coordinate of the top of the rectangle. And so we'll write then okay? Now imagine that whole thing, right? Remember, you're going to revolve the entire region around. Okay, imagine that whole thing filling up with all of those discs. And there's so many of them, gang, and they're so very thin that they actually blend into each other. You can't distinguish one from the other. And the whole thing creates this solid, okay? All right, so I think we can argue pretty successfully then that the total volume of this solid is going to equal the sum of all of those individual elements. And all of those elements are going to range, in this case, from x is equal to 0 to x is equal to 7. And all of those elements are given by this expression. So to find the total volume of this solid, it's going to be a straightforward integration problem. Okay, so we use our fundamental theorem, input the 7 first. To get our final result. Okay, so that's what we'll be doing in this section. We're going to be calculating, well, they may ask us to find area, so we already know how to find the area, but definitely we're going to be finding volumes of solids of revolution. Okay, here's another example. Okay, let's suppose we want to take the reciprocal function but only that portion of it that goes from x equals 1 to 4. Okay, so this is the reciprocal function y equals 1 over x. And it's going to be bounded by the vertical lines x equals 1, x equals 4, and the x-axis. Okay, so here's our region. And we want to take that region and revolve it around the x-axis. And when we do, we're going to generate the solid, and we want to calculate what that solid will be. Okay, so what would that look like? Let's see. Right, something like this. Okay, almost looks like a bullhorn, huh? But it's going to be solid. Okay, it's unlike a bullhorn, it's going to be solid from one end to the other. Okay, so we're going to calculate the volume of this solid. All right, so we'll proceed the same way we did in the previous example. Okay, I'm going to put a differential rectangle between 1 and 4, somewhere between 1 and 4, say maybe here. That rectangle that corresponds to that x is going to be labeled like this. Okay, take that one rectangle and rotate it around the x-axis. Okay, calculate the volume of that one differential volume. Okay, so the volume of that one disk is equal to pi times the radius squared times the thickness. Okay, say it in words every time you do these problems, gang. That way you'll never forget that little formula. It's not much, but it's worth remembering. Okay, so let's see. Now, according to our figure here, the radius is this vertical distance. Okay, the distance from the top of the rectangle to the axis. Okay, the axis of revolution. So here, that's going to give us 1 over x. And the thickness of it is going to be the same as the width of the rectangle that created it, which in this case is dx. Okay, simplify it a little bit. And therefore, we imagine that that entire solid is full of all of these vertical disks, so that the total volume is equal to the sum of all of those individual elements. And those elements range from x equals 1 to x equals 4. And those elements are represented by this expression. After that, gang, it's just straightforward integration. And so we get the following. Okay, so probably the hardest part of the problem is setting it up. Okay, if you notice though, gang, there's a theme that we've been doing here since the beginning of our applications of integration, right? And if you notice, we always start out with a differential element, and from that differential element, we find the sum of all such elements, whether it's area or volume. Okay, and that will be a theme throughout applications of integration. In this example, I'm going to take the basic square root function and I'm going to bound it from 0 to 4. Okay, so that would make this a 2. So obviously not to scale. All right, so the region is bounded by 3 equations. Y equals the square root of x equals 4, that vertical line there, and the x-axis, which is just y is equal to 0. And so now I want to take this region, and this time, I want to rotate this around the y-axis. Okay, I'm going to rotate it around the y-axis. So in this case, the axis of revolution is the y-axis. Okay, all right, so we need to be careful with the way that we put our differential rectangle. Okay, so what I'm going to do is between 0 and 2 along the y-axis, say maybe here. Okay, I have some generic y. And gang, for that generic y, the rectangle is going to be sideways that corresponds to it. Here it is. Okay, see how that works? It's sideways. But why? Why did I draw it sideways? Well, the reason is because I'm trying to get a disk out of this. Remember, this whole idea of finding these volumes is the disk method. All right, so in order to get a disk out of this, you should remember this always. Your differential rectangle has to be perpendicular to the axis of revolution. Remember that, gang. It's important. You should make a note of it, okay? In order to use the disk method, the differential rectangle has to be perpendicular to the axis of revolution. It doesn't have to touch it, but it has to be perpendicular to it, okay? All right, so here's what that's gonna look like. So it looks like I'm gonna have to go a little bit off the page there. It comes back around, so it looks like that. You have to be something of an artist, I think. And I am not an artist, but you know, we do the best we can, right? We do the best we can. All right, let's see. Now you'll notice that the disk that we've created actually has a hole in it. This kind of a disk is referred to, I'll make a note over here, it's called a washer. Okay, so a disk with a hole in it is actually referred to as a washer. Now to calculate its volume, what you're gonna do is imagine that it's a solid disk. Find the volume of the solid disk, okay? Then find the volume of the inner disk. In other words, let me use a different color. See this part that's in here, all this in here? Imagine that as one solid disk. It's a smaller one. Subtract it out and you'll have your washer, okay? So a washer is a larger disk subtracted, I'm sorry, a smaller disk subtracted from a larger disk. Okay, so let's see what that's gonna look like. Okay, so the volume of just this one differential washer. Okay, let's say pi times the outer radius squared. Now notice that the rectangle, gang, the differential rectangle is horizontal. That means its thickness is no longer dx, but in fact is dy, okay? So we'll have a differential dy and then minus pi times the inner radius squared times dy. Okay, let's see. So let me refer to my diagram. Notice, because look at this. That horizontal distance right there, that's the outer radius. Let's use a capital R to distinguish it, okay? What is the outer radius, the larger radius? In this case, it's 4 units, okay? The inner radius, however, that's this right here. Let's call that little r, okay? The inner radius. Now, you may have noticed that when I drew the first differential rectangle in there, I forgot to do what we always do, which is to label both ends of it, okay? Let me fix that right now. This end is going to be 4y. This other end, okay, well, what's that x coordinate going to be? Well, I can get that from my equation right here, because look, I can get that from here. Solve this equation for x. I'm going to say or x equals y squared. And that's going to be my x coordinate right there, okay? All right, so let's continue on with finding the volume of this washer to get the following. Okay, now the outer radius we already said was 4 minus. Now the inner radius, what is that horizontal distance? What's the value for little r? Yes, good, y squared. Y squared, very good. All right, I'll clean that up a little. Okay, And the next thing I'll do, gang, just in the interest of time, I'm going to factor out the pi, because it's a common factor, and the dy as well. Okay? Now, we imagine that the entire solid swept out by this region is going to be full of all of these washers, some larger, some smaller. But the total volume is going to equal the sum of all of those individual elements, and they will all range from y equals 0 to y equals 2. And all of those elements are given by this expression. Okay, and then after that, it's just straightforward integration. It's the setup that takes the most amount of time. Okay, all right, let me go back up here a second. Let me maybe go over here off to the side. What would this look like? Let me see. So we got this little shape. We got the shape like this, right? We're going to revolve it around the axis. Here's our axis. What's that going to look like? I don't know, maybe like a vase or something. Oh, no, not really. I don't know. What would that, maybe an ashtray, huh? Looks like an ashtray, right? It's kind of hollow in the middle. So it looks something like this. And what we're doing is we're calculating the volume of that solid of revolution, okay? Okay. This time, let's do this. Let's do the basic square root function again. And let's do the basic squaring function underneath of that. And here's the region. Okay. And let's take that region, rotate it around the x-axis. Okay, find the solid of revolution. All right, let's see. Well, we know that these we can solve, you can verify. They're going to meet up at x is equal to 0 and x is equal to 1. Oops, that should be a 1. So what I'll do is I'll put my differential rectangle in there somewhere between 0 and 1, say maybe here. Okay, I'll label the top and the bottom of it. Okay, so that's my differential rectangle. It's vertical. It's perpendicular to the axis of revolution. In this case, the axis is the x-axis, okay? And its thickness is going to be dx, okay? Let's actually draw the shape, though. I think you probably see it right away. There's going to be a hole in it. Okay, and so we're going to have a washer again. All right, we'll have a washer. All right, so you should make a note. This distance right here, that's going to be our inner or smaller radius. I'll call that r. Again, can you tell me what that inner radius is? What's the distance between the bottom of the rectangle and the x-axis? What is that vertical distance? Yeah, good. It's x squared. It's the y coordinate. Okay. And then this one up here, right up there, this distance, that's going to be your outer or larger radius. Okay, so what's the distance between the top of the rectangle and the axis of revolution? What is that vertical distance? Yeah, good. It's the square root of x. Okay, let's calculate the volume of this one washer. Okay, so it's going to be pi times the outer radius, I'll just call it capital R, times the thickness, minus pi times the inner radius squared times the thickness. Okay, so in this case, it's going to give us, let's see, the outer radius was the square root of x. We'll square that. The inner radius was x squared. Don't forget to square that. And then I'll simplify it like we did in the previous example, and I'll factor the pi and the dx out as well. Okay, so now, gang, now the total volume is equal to the sum of all of those individual washers that are going to make up the whole solid. And they will range, in this case, from x equals 0 to x equals 1. And all of those elements are given by this expression. Okay, and it's straightforward integration after that. And maybe we'll carry this one out. Notice there's a variable x in both terms, right? You've got x squared over 2 and x to the 5th over 5. That means that that 0 down there isn't going to contribute anything to the answer. It just comes down to the 1 then, huh? Okay, so once we plug in the x is equal to 1 for both x's, we can then simplify further. Okay, to get our total volume.